Introductions to Solutions in Aqueous Reactions, Gas Evolution Reactions. In this tutorial, we will be going over what is a gas evolution reaction, compounds that undergo gas evolution reactions, acid-base reactions resulting in the formation of a gas, along with some worked examples, acid-base reactions, insoluble solids in acidic solutions, and also some more worked examples. So what is a gas evolution reaction? This is a reaction where two aqueous solutions combine together to form a gaseous product that bubbles out of solution. Overall, there's two types. The first is where a gas is formed directly as a result of a double replacement reaction. So for example, we have some sulfuric acid. It is reacting with lithium sulfide. Double replacement reaction occurs. The hydrogen from the sulfuric acid and the sulfur from the lithium sulfide come together and they form hydrogen sulfide gas, which will bubble off and there's no intermediate. The second type of gas evolution reaction is where an unstable intermediate is formed first and then quickly decomposes into more stable compounds where one is a gaseous product. Now, I've mentioned these specifically before in previous videos. Now we're going to go into some more detail on them. So let's say we have hydrochloric acid and sodium hydrogen carbonate. The hydrogen from the hydrochloric acid and the hydrogen carbonate from the sodium hydrogen carbonate come together to form an intermediate. This intermediate is carbonic acid, H2CO3. Carbonic acid is an unstable intermediate product and will automatically be broken down to form water and carbon dioxide. So I would not put this in a double replacement reaction. Instead, I would say to myself, this is unstable and it's automatically going to form water and carbon dioxide. What else should you know about gas evolution reactions? Many, not all, but many gas evolution reactions are also acid-base reactions. So the type of compounds that undergo gas evolution reactions, many times they're going to involve the following polyatomic ions. So we know that the sulfide ion is a weak base. If you have an acid reacting with a compound with the sulfide ion in it, it won't form an unstable intermediate, but in a double replacement reaction, it could form hydrogen sulfide, which is our gas, and there will be no more additional products. If the compound has the carbonate or the hydrogen carbonate ion in it, which again are also weak bases, and reacts with a compound that has an acidified hydrogen, it will commonly make H2CO3, carbonic acid. That carbonic acid is very, very unstable and will automatically break down into carbon dioxide and water. If you have a compound with the polyatomic HSO3-2, the sulfite ion, or HSO3-1, hydrogen sulfite, it will form the unstable intermediate H2SO3, sulfurous acid, which will break down into sulfur dioxide and water. The ammonium ion, which is a weak acid, if it were to combine with something that has a hydroxide ion in it, it will form ammonium hydroxide, which is also extremely unstable and will break down into ammonia and water. Let's see some of this in action. Solutions of sodium carbonate and hydrochloric acid are mixed. So sodium carbonate is composed of Na plus 1 and CO3 minus 2. When we cross these down, we'll get Na2CO3. So that's sodium carbonate, hydrochloric acid plus HCl. And we know that these are all in aqueous solutions because it says solutions of, and we can assume that our solvent is water. Okay, so double replacement reaction here. So we have H plus 1 and Cl minus 1. So let's go with the easy one first. Na plus 1 and Cl minus 1 is going to form NaCl plus. Now, here's where we need to pause for a moment because our other two ions that are coming together are H plus 1 and CO3 minus 2. And when we cross these down, we're going to get H2CO3. And we're not going to write this in our molecular formula. Instead, we're going to say to ourselves, hey, this is unstable. And when this is unstable, it's going to automatically form H2O plus CO2. So if we put phases in here with this, we'll say NaCl, we know that's a very strong electrolyte, so AQ, we know that's going to dissolve, plus H2O, so that's our little L for liquid, that's an L, plus CO2 gas. So there's the gas that we're looking for right there. Now we're going to go back and we're going to say to ourselves, are these strong acids, weak acids, strong bases, weak base, strong electrolytes? What do we have going on here? Na2CO3, strong electrolyte. HCl, strong acid. NaCl, strong electrolyte. Water, well, water is water. We're not touching that, and carbon dioxide is a gas. So when we think about the complete non-ionic equation, we're not going to touch those at all. That's what's driving this reaction forward. So, the next thing I need to do, goodness, I need to balance this thing. So 2 NAs, can't believe I almost forgot that. 2 Cls, do my hydrogens balance? Yes. Do my oxygens balance? Yep, we're looking good. Now that we know that, let's do our complete ionic equation. So 2Na plus 1 plus CO3 minus 2 plus HCl is a strong acid, so the 2 is distributed. 2H plus 1 plus 2Cl minus 1. And these are all aqueous. NaCl is a strong electrolyte, so 2Na plus 1 plus 2Cl minus 1 plus H2O liquid plus CO2 gas. Excellent. Now we're going to go through and we are going to cancel out our spectator ions because we don't need those. And I'm only seeing one. 2Na plus 1, 2Na plus 1. Oh, I saw another one. 2Cl minus 1, 2Cl minus 1. So CO3 minus 2. Nope, that's not over there. 2H plus 1. Nope, that's not over there. Hey, we just canceled out our spectator ions. So now I'm just going to rewrite this. So CO3 minus 2 plus 2H plus 1 yields H2O liquid, that's an L, plus CO2 gas. And again, we know that these are in aqueous solutions, so I'll put the little AQs in, but really you do not need to include the state symbols, but it does really help to include them to make sure that you're not forgetting whether something is a liquid or a gas. Let's look at another example. Solid, got to keep that in mind here, copper 2 sulfide and a solution of hydrofluoric acid are mixed. Okay, solid copper 2 sulfide. So that's Cu plus 2. Sulfide is S minus 2. So when we write our formula for that, it's going to be CuS plus a solution of hydrofluoric acid. Well, hydrofluoric acid is just HF aqueous. AQ. Now, you see how it starts with solid, and we're going to talk a little bit more about this later on in the video, but if something is listed as solid as a reactant, we got to keep that together no matter what, all the way through the reaction. So if something starts as a solid, you got to keep it as a solid. There is an understanding that both of these can be treated as ions that are part of a reactant and will be a driving force forward a little bit, but if it starts with solid, you got to keep it solid all the way through. Okay, when this reaction happens, what's going to happen? Well, we have H plus 1 and F minus 1. So let's take the Cu plus 2 and put it with the F minus 1. All right, CuF 2. Fantastic. AQ plus, and then we have H plus 1 and S minus 2. That's going to be H2S, and that is our gas. This is a situation where we have a gas. Notice here it is a strict double replacement reaction. No intermediates are formed. It's going straight to H2S. Okay, now let's go on and balance this. So I have 2 fluorines, 2 fluorines, 2 hydrogens, 1 sulfur. The coppers are balanced. Okay, next thing that I want to do is I want to go through and I want to talk about each one of these in terms of writing out my complete ionic equation. CuS is a solid. If it is a solid, we're just keeping it as a solid and we're not breaking it down. HF is a weak acid. We're also not going to touch that either. CuF2, we're going to call that an electrolyte. So let's just give that an electrolyte name, and that will dissociate. And then H2S is our gas. We are not doing anything to that. So when we go on and we write our complete ionic equation, CuS solid is going to stay together, plus 2HF aqueous is our weak acid. We're not touching that either. Okay, and then we're going to have Cu plus 2 plus 2F minus 1. We're going to give AQs to both of these. And there might not be much of it in solution, but we're going to acknowledge that there are some of these ions here, plus H2S gas. And we're not going to break that down. See, the only thing that we really dissociated was the Cu plus 2 and the 2F minus 1. And if we look at our complete ionic equation, there are no spectators. This is it. This is also our net ionic equation. So on a homework or on a test, it is absolutely fine to say, if you get to this situation, you can write same as above and not have to rewrite it. That is absolutely acceptable. So this is a situation where we have a double replacement coming together between a sulfide ion and a hydrogen ion to produce the gas H2S. Let's look at another example. Solutions of potassium sulfite and nitric acid are mixed. Let's start with potassium sulfite. So we're going to have K plus 1. Sulfite is SO3 minus 2. Nitric acid is H plus 1 coming together with NO3 minus 1. This is a double replacement reaction. So we have K plus 1 and SO3 minus 2. When we write the formula for that, it's going to be K2SO3 plus nitric acid, which is H plus 1 and NO3 minus 1. So that's just going to be HNO3. Again, both of these are aqueous because they're saying solutions of yields. The K plus 1 and the NO3 minus 1 are going to come together to form potassium nitrate, KNO3 aqueous. And then we have the H plus 1 and the SO3 minus 2. And when we look at that, we know that's going to form the formula H2SO3. H2SO3 is one of those very unstable compounds that we've just talked about, and it will automatically break down into H2O and SO2. So we're not going to write H2SO3 in our molecular equation. Instead, we're automatically going to go to our more stable products of H2O liquid plus SO2 gas. Excellent. Now we're going to balance this. So we have 2 potassiums on the reactant side. I'm going to put a 2 in front of the KNO3. We have 2 nitrates on the product side. So I'm going to put a 2 in front of the HNO3. So 2 and 2 and 2, 2. Looking at what else we have here, I have SO3. Well, I have a single S here, so that's good. 3 oxygens total on my reactant side. 1 plus 2 gives me 3, and then my hydrogens are also balanced. So that's great. I have a properly written and balanced molecular equation. The next thing I'm going to do is go through and identify what I'm working with here. So K2SO3 has a group 1 metal in it, so that's a strong electrolyte. HNO3 is a strong acid. KNO3 is a strong electrolyte. Water is just water, not touching that. And SO2 is a gas, molecular compound, not touching that. Now that we've gone through that process, we're going to write our complete ionic equation. So 2K plus 1, that's coming from our subscripted 2 above, AQ, plus SO3 minus 2, AQ, plus nitric acid is a strong acid, so that's going to fully ionize, 2H plus 1, AQ, plus 2NO3 minus 1, another AQ, yields 2K plus 1, AQ, plus 2NO3 minus 1, another AQ. And then we get to our water. So H2O liquid. Not going to mess with that. And sulfur dioxide, SO2 gas. All right. Now we can go through and we can cross out our spectator ions. And we do have quite a few spectator ions here. So 2K plus 1 cancels 2K plus 1. 2NO3 minus 1 cancels 2NO3 minus 1. The SO3 minus 2, that's not a spectator. The 2H plus 1 is not a spectator. I think we're good to go. So we're just going to rewrite our net ionic equation as SO3 minus 2 plus 2H plus 1 yields H2O, which is our liquid, and SO2, which is our gas. And I guess for the sake of doing this, we should be really good and put all of our phases in. But I'm not expecting you to put phases in on tests or quizzes or homeworks, because that's not how the AP grades. Great, so that's our net ionic equation with the production of sulfur dioxide as a gas. Last example of a gas evolution reaction. Solutions, so again we're going to assume this is an aqueous solutions, of ammonium chloride and potassium hydroxide are added together. So ammonium chloride, that's composed of NH4 plus 1. Chloride is Cl minus 1. Potassium hydroxide, that's K plus 1. Hydroxide is OH minus 1. Okay, knowing all this, ammonium chloride is going just to be NH4Cl plus K plus 1, OH minus 1, that's just KOH, arrow. And then the NH4 is going to go with the OH. Let's talk about that in a second. The K plus 1 and the Cl minus 1 are going to come together and form KCl plus. All right, now let's talk about this. NH4 and OH are going to come together to form ammonium hydroxide, which is our last unstable intermediate that we have talked about. NH4OH is automatically going to break down into ammonia, NH3, and water, H2O. So just like I've stated previously, I would not put this in my molecular equation. Instead, I would recognize the fact that it is unstable, and I would write the ammonia, NH3 gas, and the H2O liquid as part of my molecular equation. Now let's go through and talk about solubilities. All right, NH4Cl is very soluble, so that's strong electrolyte. KOH is a strong base, so that is going to dissociate very, very easily. KCl, strong electrolyte. NH3, well, that's a gas, so that's just G for gas. Don't touch that. and water is a liquid, so don't touch that either. Now let's go back and see if we need to balance this thing. One nitrogen, one nitrogen. How many hydrogens total we have here? 4, 5, 3. Okay, so our hydrogens, there's the same amount on both sides. One chlorine, one potassium, one oxygen. Hey, we don't need to balance. Beautiful. All right, so let's go on and write our complete ionic equation. So the first thing we're going to do is write NH4 plus 1, and we know this is all aqueous, plus Cl minus 1, little aq, plus K plus 1, all aqueous, plus OH minus 1, aqueous. And you really need to talk to your teacher and find out, do they want you to include the phases or not? I'm putting it in here right now because, many different people might be watching this, but I'm not a huge stickler on making sure that everything that's soluble in water is labeled as AQ. But, I don't think it's the worst habit, especially when you start getting into different phases. Like NH3 we know is going to be a gas, and H2O is going to be a liquid. So it is good to go through and label those just to make sure that you don't forget the fact and you don't try to dissociate / ionize any of these. Okay, let's go through and look at spectator ions. So Cl minus 1, that's a spectator. K plus 1, that's a spectator. But I don't believe anything else is going to be a spectator. So now we're just going to write our net ionic equation. That basically leaves out those spectator ions. So only the ions and molecules that are involved in the reaction will be involved in our net ionic equation. NH4 plus 1 plus OH minus 1 gives us NH3 and H2O. And that's our net ionic equation, where we are forming ammonia and water as a product from the very unstable molecule NH4OH. Now let's talk about acid-base reactions, insoluble solids, and acidic solutions. And technically, we've already done one example, but let's look just at 2 more. Many ionic solids that exist do not dissolve to a great extent in water. These solids are given a general classification of insoluble. But note to self, no solid is completely insoluble. All solids will dissociate to some degree, which later on will be defined as KSP. And when I'm talking about no solids, I'm talking about ionic solids. When such solids react with acids, however, the reaction is driven towards products when water is formed as a product, a neutralization reaction, or a gas is formed as a product, a gas evolution reaction. And let's look at 2 examples of that. Solid barium carbonate is added to a solution of acetic acid. So in each one of these situations, we're going to be starting out with one of our reactants being a solid. Write the formula, put it on the molecular equation line, don't touch it again. So barium carbonate, barium is Ba plus 2, carbonate is CO3 minus 2. Acetic acid, we're going to write it in the inorganic way, so HC2H3O2, that's a 2. All right, so I have my 2 reactants, so it's H plus 1. I was getting a little involved there. C2H3O2 minus 1. So when I write out these formulas for my reactants, Ba plus 2, CO3 minus 2, that's going to be BaCO3 solid, plus acetic acid, which is a solution of acetic acid, so that's just going to be HC2H3O2, aqueous, because it's saying a solution of. Okay, when we look at our products here, the Ba plus 2 is going to go with the C2H3O2 minus 1, so it's going to be barium acetate, Ba, parentheses, C2H3O2, with a subscripted 2 down here, plus, we have H plus 1 and CO3 minus 2. We know that's going to form H2CO3, and we just came off of this. We know we can't write H2CO3. Instead, we have to write H2O and CO2. So H2O is our liquid. This is what's helping to drive this reaction forward. And CO2 is our gas. Now let's go through and balance this thing. So we have C2H3O2. We're going to put a 2 in front of here. So we balance these 2 out. 2 and 2. 1 barium, 1 barium, 1 carbonate. Well, we can't do 1 carbonate because that polyatomic doesn't exist on the other side. So 1 carbon, 1 carbon. How many oxygens total here? We have 3. So 3 oxygens totals, that's balanced. 2 hydrogens, 2 hydrogens. Fantastic. So now we've just balanced it. Let's go through and label our solubilities on here. Now BaCO3, that's a solid. Don't touch it. HC2H3O2, you should know that that is a weak acid. We are also not going to ionize that. Now BaC2H3O2, because we have to realize that all of these reactants will, to a very, very, very tiny degree, ionize, dissociate. So we do have to predict that some BaC2H3O2 is going to form. That is going to be a strong electrolyte because the acetate ion has evolved. H2O is a liquid, CO2 is a gas. All right, let's talk about writing our complete ionic equation here. So BaCO3 is a solid. That's not going to break down. Plus 2HC2H3O2. This is aqueous, but it is a weak acid. Don't touch it. Weak acids and weak bases, don't break those apart. Now, BaC2H3O2, that's a strong electrolyte. So this is going to dissociate into Ba plus 2 and 2C2H3O2 minus 1 plus H2O liquid and CO2 gas. And then we're going to put little AQs on both of these because we know they are going to be, even though their concentrations might be small, they're still going to be present. Now I'm going to look back through and I'm going to look for any spectators, and there are no spectators, so there's nothing to cross out. So what do we do in this type of situation? We write same as above for our net ionic equation, and we can move on. We are left with our complete ionic equation. There is nothing to break down here. We are good to go. Last example, a solution, again, we're going to consider our solvent to be water, of hydrochloric acid is added to solid copper 2 hydroxide. So hydrochloric acid is composed of H plus 1 and Cl minus 1. Solid copper 2 hydroxide. So copper, Cu, Roman numeral number 2, so that gives us a plus 2 charge. Hydroxide, OH minus 1. So when we write out our formulas here for our reactants, we're going to write HClAQ plus CuOH2. Then the Cu is going to go with the Cl, so CuCl2 plus H2O. Now I'm going to go back and I'm going to balance this. So 2 chlorines. I need 2 chlorines over on my reactant side. 1 copper, 2 oxygens. I need 2 oxygens over on my product side. So now my oxygens are balanced. 4 hydrogens right here, 2 here, 2 here. Everything's balanced. Now I'm going to go through and I'm going to say to myself, what am I working with? HCl we know is a strong acid, so we're going to put Sa up here. That will ionize. CuOH2, they're telling us it's a solid. If it's solid, it's not going to break down in our molecular equation. We're not going to break it up into ions. CuCl2 is soluble. That's a strong electrolyte. And then water's water. L is for liquid. Fantastic. So now we're going to write our complete ionic equation. So 2H plus 1 plus 2Cl minus 1, and I should be putting my AQs in for both of these, plus CuOH2. That's a solid, so we're not going to break that down. CuCl2 is a strong electrolyte, so Cu plus 2 plus 2Cl minus 1. We're going to put little AQs for both of these. And then finally, 2H2O, which is our liquid. The next thing that we're going to do is we are going to cross out our spectator ions. So 2Cl minus 1, 2Cl minus 1. There are no other spectator ions in our complete ionic equation. So we're going to finish this up by just rewriting our net ionic equation. 2H plus 1 plus CuOH2 because it is a solid. Cu plus 2 plus 2H2O liquid. Fantastic. And that is our net ionic equation for a reaction between hydrochloric acid reacting with solid copper 2 hydroxide. So what did you learn in this tutorial? We went over the definition of a gas evolution reaction. We looked at compounds that undergo gas evolution reactions. We talked about acid-base reactions resulting in the formation of a gas, along with some worked examples. Then we talked about acid-base reactions that involved insoluble solids in acidic solutions, and wrapped it up with some more worked examples. Need more help? Feel free to contact me. Have a great day.